last time we did a lot of review about method of undetermined coefficients. So I hope by now, if you see a problem like that, you'll have a good sense of what to do. And there's a good chance you might see a problem like that again at some point in the future. But there's another thing we talked about last time, which is variation of parameters. And it kind of has a similar flavor of the method of undetermined coefficients, where really we're trying to find two functions, u1 and u2, such that u1 times y1 plus u2 times y2 in a second order differential equation is the solution. So you can think about, oh, it's like we have these coefficients, they're now coefficient functions. We just need to determine them. But of course, you know, it's a little bit more fun than just guessing. So what's the full idea? If we have a second order differential equation, y double prime plus p of x y prime plus q of xy equals f of x, and we know y1 and y2, which are linearly independent solutions to the corresponding homogeneous ordinary differential equation, then we can say that y is minus y1 of x times the integral y2 of x f of x over the Wronskian of y1 and y2 plus y2 of x the integral y1 of x times f of x over the Wronskian times y1 and y2. And when we're actually doing these problems, this is called variation of parameter problems, we just start here. We don't go through the derivation. That takes too long. Now, as you look at this formula, you'll notice a couple things. You know, there's a Wronskian downstairs in both pieces. There's an f of x upstairs in both pieces. And then one part has y2 on the inside, y1 on the outside. The other one has y1 on the inside, y2 on the outside. So it's not the worst thing to memorize. There are worse things to memorize, but most of the time we'll just say, let's look it up. Now, as you stare at this for a second, though, you might say for a second, hey, I see where f of x is showing up. Where does p of x and q of x show up in this formula? I don't see any p of x and q of x. So where is it at?
The specific solution, y1 and y2.
All right, so someone has said, it's inside the solutions for y1 and y2. And that's where they are, because p of x, q of x influences what y1 and y2 are, and so that's how they show up in the answer. All right. Now, we only talk about second order differential equations for this method. We could do third order using the technology we talked about last time. It comes down to a variation of Cramer's rule. It gets more complicated. We won't never do it in this class, but it can be done. It can be done. We have the technology to do it. We just won't choose to do it. Whereas the second order takes up this much of the screen, the third order takes up, you know, that much. So we're not going to do it. All right. Well, let's do a problem. And we have one. So find the general solution for y double prime plus y equals tangent of x. So where do we start in a problem like this? Okay, so we look at the homogeneous equation. Y double prime plus y equals 0. Feels really familiar. We may have seen this before. All right, what's the equation in terms of the characteristic polynomial? R squared plus 1 equals 0. What are the roots? Plus or minus I. What are the functions? Y1. Sorry, what? All right. So cosine and sine. Now, people will probably say, wait, why are you writing it this way? Don't we normally write it in this format? YC equals some constant cosine of x plus some constant sine of x? Well, we often do write it that way when we're talking about the form of the complementary solution, but right now we're trying to grab the pieces. So we say, okay, first function, second function. So we're just grabbing the individual functions. Now, we can pause and say, is that the only possible answer that we could give for y1 and y2? Now, of course, there's the cheating thing, like, oh, we'll just switch. We'll call y1 sine, y2 cosine. Okay, but is that the only possible things you can do? What do you think? Okay, a yes, and then followed by a no. All right, cover the bases. All right, if I say all the possible answers, one of them will be right. Partial credit. So it turns out that there's actually many possible things that you could do. I could, for example, say y1 is cosine of x plus sine of x, and y2 could be 100 sine of x. Those are two independent solutions to the differential equation. So you might say, well, why do we go with this one? Simple. Yes, you nailed it. Make your life easy. We love ourselves. And so because we love ourselves, we're going to say, let's pick the simplest possible functions that we can. And so for this one, cosine and sine are the simplest possible ones. Not the only ones, but the simplest ones. All right, so now that we found y1, y2, that's good. What's probably a next thing we should find? Wronskian. Because that's going to be sort of the hard piece here. Because the Wronskian is, in the denominator. So, and it shows up twice. So we should take some care. So we're going to take the Wronskian of cosine of x, sine of x. Okay. So this is going to be a 2 by 2 determinant because there's two functions, so 2 by 2. In the first row, you put the functions themselves, cosine, sine. What's in the second row? Minus sine of x cosine x. Where are these coming from? Derivatives. Good. Now, take our determinant here. Go diagonals. Cosine times cosine. Cosine squared. Other diagonal. Minus sine times sine. Minus sine squared. But, remember we subtract it. So you add the one going down, subtract the one going up. So you have cosine squared x minus negative sine squared x, also known as 1. Oh, what a beautiful Wronskian. Great Wronskian. I like this one. All right, well, now we're ready to begin. And we'll just follow the formula. So we're told that y is equal to minus y1. Okay, so that's minus cosine of x, integral y2, that's sine of x, times f of x, and of course f of x is this tangent of x, so times tangent of x divided by the Wronskian, which is 1, plus y2, that's sine of x, integral y1 cosine of x times tangent of x, which is our f of x, divided by the Wronskian dx. Okay. Great progress. 2 integrals. We just have to do these 2 integrals and life is good. Which integral do you want to tackle first? The second one? Why do you want to tackle the second one? What's happening here? Cosine x times tangent x? Oh, cosine x times tangent x, also known as sine x. What is the integral of sine x? Negative cosine x or positive cosine x? Yeah, negative. Negative. I know a lot of people are like, wait a second, now I'm not sure. Okay, so that wasn't so bad. That was pretty straightforward. We're halfway done. Oh, wait a second. Hold on. We forgot something. Plus c. So let's put our plus. And for some strange reason, I'm going to put the letter d here. But again, it's just a constant. We'll come back to why I put that letter d. Because I do want to talk about what that constant means and whether or not we need it. And we'll get to that conversation as we get towards the end. Okay, 1 integral down, 1 integral to go. I think the next integral will be more fun. All right. And I suspect that because people are like, let's skip it. So We're not going to skip it. How do you integrate sine of x times tangent of x? Sorry, what? Rewrite it? How can we rewrite it? Sine squared times what?
Sine squared x times tan x.
How about, I do agree with sort of a philosophy here. See, because there's a clue, it involves trigonometry. And whenever you have a problem involving trigonometry, you start thinking, let's think trig identities. And if you have sine and tangent, they really don't go together very well. Like tangent and secant, they blend. They're wonderful. It's like pumpkin spice in October. You know, they go together. But sine and tangent, no. So what can you do? If you're ever stuck with a problem where you're integrating trig functions and you don't know what to do, put everything in terms of sines and cosines, because sines and cosines go great together. So this could be sine squared x over cosine of x. And now just say, okay, let me think about this integral. Sine squared over cosine. So, someone has said, there's an identity. Yes, there's a million identities. But for trig, you only need to know 6. Okay, suppose I can count 6. There we go, 6. Is there a good identity here? What? 1 minus cosine squared has been suggested. And since I'm writing it down, I must believe in it. Now, this is not the only way to do this integral, but it's the only way to do it without having too many tiers. 1 over cosine, secant. Cosine squared over cosine, cosine. Now, do we know how to integrate those two functions? How about cosine? Do we know how the integral of cosine? Yes. What is it? Sine. Do we know the integral of secant? Yeah, not as much positive enthusiasm about that integral. Okay, so we have here the minus cosine x in the front. Then we have to do this integral. Okay, so time to demonstrate our knowledge. Integral of secant? Natural log secant plus tangent. Now you might be wondering, how do we know that? And the answer? It's on our list of 10 things to know. That's a short list. You know how many things are on that list of 10 things to know? 10. Yeah, that's not a big number. We can handle that. Integral of cosine? Sine, and the minus will come along. And then plus c. Okay, so there's y. Well, let's clean it up a little bit. So you can say, okay, so there's the minus cosine of x times the natural log secant x plus tangent of x. All right, we have that. Then we have minus cosine x times minus sine x. What does that become? Cosine x sine x. What do we have over here? Minus cosine x sine x. So what happens? They cancel out. Cool. Okay, now we have c times cosine x. You might say there's a minus, but what can we do with that minus? Put it into the c. C is good at absorbing constants. So c cosine of x. And then this other constant, d sine of x. Now, have we seen c cosine x plus d sine of x anywhere else? Yeah, up here. So this part, this is the y sub c. In other words, that's the part coming from the homogeneous solution. And so now we get to the answer, what do these constants do? If you leave the constants in there, you will have the homogeneous part of the solution pop out. If we didn't leave the constants in there, what would we be left with? We'd be left with the particular part. So if you're just after the y sub p, you can assume your constants are 0. If you want the whole thing, either assume the constants are 0 and don't forget to add it in, or just leave the constants in there right now and then it comes out anyways. But we want the whole thing. So there we go. There we go. Minus cosine x times log of secant plus tangent. Beautiful, beautiful. All right. How'd you feel about that one? Good? Great. Well, let's do another one while we're in the mood. Okay. So again, we'll have the formula for reference so that we can all agree what's going on. And we're asked to find the general solution for y double prime minus 2y prime plus y is e to the t over 1 plus t squared. Now, I don't know about you, but when I look at this problem, my heart starts to beat a little bit faster. Yours might be beating a little bit faster too, but not out of love, out of nerves. I see it, something, and I say, oh, what do I anticipate coming up? Yeah, I just feel it in my heart of hearts. There's an arctangent, which means this is a great problem. Well, I hope. I've been burned before. But let's find out what happens. Okay, so where do we begin? Homogeneous part. Y double prime minus 2y prime plus y equals 0. Characteristic equation for that. What do we have? R squared minus 2r plus 1 equals 0. And someone said, hey, that's a nice thing. It factors to r minus 1 squared equals 0. So what are the roots? 1 and 1. Repeated root. That's cool. What's our first function going to be? E to the t. Because our variable is t. Now you might say, how do you know your variable is a t? Because I'm pointing at it. There's a t there. Now you might say, but wait, Steve, this equation all involves x's. Are you saying it also works if we put t's? Yes. X is just a symbol. I could put smiley faces up here and it's still true. But I'm not that cool. So I'm not going to. What's our second solution? T e to the t. Now again, you could come up with other combinations of these for y1 and y2, but simple. That's the goal. Okay, so we have our two functions. All right, let's jump in to the Wronskian, because that seems to be our next part. So we're going to compute the Wronskian, e to the t, and t e to the t. All right, 2 by 2, nothing too crazy. First row, just write down the functions. Derivative of e to the t, e to the t. This next part. On the exam, there were so many answers. Some were creative, some were head-scratching. There were even correct answers. Now, don't be creative. Be correct. You know, if you want to be creative, art history, that's a wonderful place. But this is math. We got to be careful here. Okay, so what's the derivative of t e to the t? Okay, I think it sounds like most people got it. So what's the rule? Let's just say that. Product rule, good. So it's the derivative of the first times the second, which would be e to the t, plus the first times the derivative of the second. So we could do a couple things. So if we want, we could write it like e to the t plus t e to the t. We could factor out e to the t if we wanted to. It's just how we feel. Okay, so now our determinant. So we're going to get e to the t times e to the t plus t e to the t, right? Multiply going down. Subtract e to the t times t e to the t. Multiply going up. Now, should we stop here with the Wronskian?
Simplify.
Yeah, simplify. Now, why do we want to simplify the Wronskian?
That looks gross.
Well, it looks gross, but also, where is the Wronskian? In denominators. You want the denominator to be the most beautiful, clean, simplest thing you can make it. anytime you have something downstairs, it's like, I will make this into a work of art. If it's upstairs, it's okay. Doesn't matter. But downstairs, we care. Okay, let's multiply this out. E to the t times e to the t. E to the 2t. E to the t times t e to the t. T e to the 2t. E to the t times e to the t. D e to the 2t. What do you see? Cancellation. Almost as if it was meant to happen. Because it was meant to happen. So that's a pretty straightforward Wronskian. That means we have a chance. A real chance to answer this problem. All right, so we begin the real work. So our function we're after, minus y1, so minus e to the t, integral y2 t e to the t times the function f. So here, this is our f. So times e to the t over 1 plus t squared. All of that divided by the Wronskian, e to the 2t dt, plus our second function, t e to the t, integral, our first function, e to the t, times our function f, e to the t, or 1 plus t squared, divided by our Wronskian, e to the 2t, dt. And yeah, we just have to integrate that. But I suspect it'll simplify. How about this first integral? Does anything cancel? You have e to the t times e to the t upstairs, which is e to the 2t. Downstairs, e to the 2t. Cancel. How about here? Same thing, they say. Because it's true. Same thing happens. So what's left in the first integral? The t over 1 plus t squared. Plus t e to the t. Second integral, what's left? 1 over 1 plus t squared. All right, now one of these integrals is on our list of 10. That's how cool it is. It made the list. It's part of the in crowd. The other integral got close, but didn't quite make the list. Well, let's do these in order. How do you integrate something like t over 1 plus t squared? Substitution? Okay, how would that work? Okay, so if you let u equal the denominator, 1 plus t squared, the derivative of 1 plus t squared? 2t. Ah! But there's just a t up here. Okay, now there's a 2. But wait a second, you can't just put a 2. Now we can, right? So half times 2 is 1. And so what you have is the 2t dt would be the du if this part down here were the u. So what does that end up being? So we have the half, e to the t, and then natural log, 1 plus t squared. And I'm not going to worry about the plus c because I know that's going to go into the homogeneous part. All right, the second piece, t, e to the t, and of course, arctangent. I know. We knew it was coming. So that's it for the particular. We want the general. So the last thing is we add in our pieces from the homogeneous. So plus some constant, e to the t, plus some other constant, t e to the t. And we're done. Woohoo! All right, how are you feeling about this variation of parameters? And other than there's a crazy formula, anything else sort of like make you nervous about the problem?
What's next?
What's next? Not variation of parameters. No. You love variation of parameters that much? It's like, I want more variation. Well, too bad. Because we do have a different topic to talk about. So we're switching to systems. And so this really is a big switch in our class. And so you can think of it as sort of 3 or 4, depending upon how you count major topics. So variation parameters closes the chapter on the first part of the course. We're ready to open the chapter on the second part. So what do we mean when we talk about systems of differential equations? Well, we start by saying, well, what have we been talking about? So previously, what we looked at is we had one output, one input. So maybe x is a function of t. Y is a function of x. And we set up one equation that involved derivatives. So something like 2x double prime plus 16x prime plus 50 equals 12 sine t. This kind of equation we saw. This is the equation that came from a spring mass system, for example, where you would have a spring, a damper is involved, and there's some external force acting as well. Now we're switching to something new. And the new thing says, hey, let's have 2 or more outputs. So now there's many things changing. But not only do we have lots of things changing, it's not like we have like over here in this little box, we're going to talk about x, and over here we're going to talk about y. It's like, no, x and y can interact. And so that's sort of the interesting things. We have these outputs that are interacting with each other. So whatever x is, whatever it measures, it can affect y. And vice versa. And we say, okay, well, these things are changing. They're interacting with each other. And so we end up with not just one equation, but many equations that say how these variables relate to each other. And so here's one possibility. So x double prime equals minus 4x plus 3 times y minus x. And 2y double prime equals minus 3 times y minus x plus 5 sine of 6t. Now, we could have just written down anything. But we're starting with something that actually corresponds to an object that we can talk about. Say, oh, this kind of makes sense. So where this particular system of equations comes from is a picture like this. So what's going on here? You should think of it as there's a wall over here. And attached to that wall is a spring. Then that connects to your first little block. This block happens to have mass of 1. You can tell it has a mass of 1 because they write 1. And then there's a second spring, which is a different spring. You know, it's a little bit more loopy, maybe not quite as strong. And so you'll see that there's some k values here. So that indicates sort of the spring constant. And then you connect to your second mass, your second block. This has a mass of size 2. And then there's something over here. And the way you should think about this part is there's this external thing acting. You can think of it, maybe there's like a piston that's moving that second block around. And it's going 5 sine of 6t. That's the force that's being acted on there. An external force. Okay, so a couple of things that are happening here. What are x and y measuring? Well, you'll see that there's these little lines here. So this first little line says, if your springs and masses were at rest, this is where the first mass would lie. See how it's been stretched over? So it's moved over a little bit. So x measures how far off the first block is from where it would want to be at rest. The second line here, that's where y would want to be if it was at rest. So y measures how far off the second block is from where it wants to be. And now we say, well, what's going on here? Well, the blocks are connected to each other. There's a spring connecting to them. So if I move a block, it will affect the other one. So it's not just like, okay, x, that first block, lives in its own world. No, there's some relationship going on with y. And so now the question is, how do we find those relationships? So here's what we can do. we start by thinking about these equations and what they represent. Now, the first one, there's a little bit of a subtlety here. We see x double prime, but secretly they wrote 1x double prime. And you're like, ooh, that doesn't change anything. But what does 1x double prime represent? What?
The mass.
It's a force. Because x is a location, so x double prime is measuring what? Acceleration. So that's an acceleration. What does 1 have to do with it? It's the mass. Mass times acceleration is force. So now you have the forces. So the trick is just focus locally. What's acting on that first block? The 2 springs. And so you say, okay, focus on just the one side. Well, this one side is super easy. That's just the spring. And then when we say, okay, we have Hooke's law. And so Hooke's law says it's minus kx. That's the force. Well, k is 4, so you get minus 4x. Because x is how far off you are. Now the second one is sort of slightly more interesting. Because we have to think about what's happening to this spring. Well, we know it's going to be the Hooke's law, the constant of the spring, times this quantity here, which is how much is this spring being stretched or compressed? So now the question, how do we know how much this spring is being stretched or compressed? Well, it depends on the values for x and y. Because you can imagine if I fix y for a moment and if I fix x and I increase y, what happens? So I fix x, I let y grow, what's happening to the spring? You're stretching it. As you stretch it, what will the spring want to do? It will want to compress. So in terms of locally here, it will want to send the first object towards the right. So you can see that. If you increase y, this becomes positive, and it says, hey, move towards the right, move in the positive direction. If you fix y, and you start to move x up, what happens to your spring? What are you doing to it? You're starting to compress the spring. As you compress the spring, what will it want to do? It will want to push back. And that's why it'll say, no, go back where you came from. You're a little too close to me. There's the 3-foot rule, right? And so that's reflected in this minus x. So essentially what this quantity y minus x is measuring is, this is the amount that the second spring is being stretched or compressed. And then we just have to put that in. Okay, so that's the first spring. The second is a little bit easier. Sorry, the first mass. The second mass, okay, so mass is 2, acceleration y double prime. We have the spring on the left, basically the same idea, minus 3 times y minus x, and then the external force on the right, which is 5 sine of 6t. So it's the way you get to the system is you just say, what's happening to each one locally? And then we can use that to figure out what's happening to the system. I will say this came from the book, so if you don't find my explanation compelling, you can go to the book, and it has nicer pictures. But it doesn't have moving fingers, so it's a balance. Good pictures versus the fingers that can move around. All right. But the moral is, there are settings where it makes sense to have systems. In other words, where it makes sense to have multiple equations involved. Now, one thing that we might talk about when we talk about these differential equations is what we call the order. So the order refers to saying how many derivatives did you have to use? The highest derivative. So come over to this system of differential equation. What's the order? It's 2, right? The highest derivative is a second derivative. So we'd say it's second order. Now, what would we prefer? First order. Or 0th order would be amazing, which means we're no longer in differential equations. But okay, we're in differential equations, so we have to have something. So yeah, we'd like first order. So here's the cool thing. We can always basically reduce to first order. Now, I should say not always, but for all intents and purposes for our class, always. The only thing that could really stop us is if somehow the highest derivative was trapped in 2 different pieces that we couldn't reduce down to a single part. So if you can ever get the highest derivative by itself, then you can knock it down to a first order. And so we actually have an example. So here we have 2 systems. Now you might say, wait a second, Steve, that's not a system. It is a system of equations. It's a system involving how many equations? 1. So it's a system of 1 equation where we have a third derivative. Okay. So we can even make a note here. That here is our system, 1 equation, order equals 3. Now, what we can do is we can translate this into another setting. And my claim is this setting here is equivalent to that setting. Now, if we look at this setting here, this is a system. How many equations do we have? 3 equations, but what's the order? 1. So what's happened is we have this sort of trade-off between how many equations do we have versus the order involved. So if we're willing to introduce a lot more equations, we can get the order down. Now, is that a good thing? It can be if we have good techniques. You might say, do we have good techniques? We will. We will. Coming soon. But I haven't convinced you yet that these are actually the same. And I want to try to do that. So how should we think about this? Well, what you should think about is, in this setting here, you should really think about x1. That's your real function. That's the function I want. So that's one I'm after. How should we think about x2? Yeah, so x2 is really the first derivative. How should we think about x3? See, x3 is derivative of x2 prime. But what do we know about x2? It's x1 prime, right? So x3, running out of space, is really what? x1 double prime. So what we're doing is we're introducing a collection of new symbols, new functions, but those functions represent various derivatives. So we have the function, its first derivative and its second derivative, and now by the end we say, oh, what is x3 the same as? Or sorry, x3 prime. It's the same as the third derivative of x1. And x3, that was the same as the second derivative, and then you have x1 squared. So if you come and compare, if I just put a little 1 here, you see you have x1 triple prime is 5x1 double prime plus x1 squared plus 5. And so you're really solving the same problem. Just in the system, we're just explicitly saying, oh, and make sure you also have the function and its first and second derivatives in the meantime as well. Okay, which is why we have this statement here. We're going to spend our energy on first order systems. So if you get later on, you say, wait, this is wonderful, but what about second order? And the answer is, no, just first order. Just first order. That's all we need. So let's take this system. Here's the system of equations we just talked about. We said it's order 2. Let's turn it into a system of order 1. How many equations will we need if we turn it to an order 1? What do you think? We have 2 already. So 4 is a good guess. Okay, so what do we have? Well, Notice I want to get up to the second derivative. So let's introduce something. We'll call it x2. We'll let that be x1 prime. Or we could just say x1 prime equals x2. Now, what would we think about this? So think of this as put little ones here. So what do we do with x1 double prime? What will that be? Well, we don't need to introduce an x3. We can just do it as x2 prime. Because we only need to get up to second derivative. If we need to go up to third derivative, we'd introduce another variable. So essentially, however many derivatives you have, the number of derivatives involved -1, that's how many variables you need. You have to sort of work your way up. Okay, equals, and then on the other side, minus 4x1 plus 3 times y1 minus x1. And I should point out, you could combine the x1s together. So now, that's nice. There's only first derivatives here. Now we do the same thing over for the y's. Well, what's our next thing we need to do? Yeah, y2 is y1 prime. Or y1 prime is y2. And then 2 y2 prime minus 3 y1 minus x1 plus 5 sine of 6t. And we have a first order system with 4 equations. And there we go. Okay. So it looks like we have about a few minutes left, about 6 minutes left. Any questions on this one? The idea of going to first order? Essentially, it's not a very complicated idea. If you find your highest derivative and then you just introduce a series of variables to help you knock the derivative down one at a time. So with 6 minutes left, we should have enough time to read the next problem. We might even be able to solve it. And so it's sort of like, whoa, there's a lot going on here. Okay, that's all right. We're good. We can figure this out. So set up a system of differential equations. So hey, we get to make a system now. So we got this wonderful wall of text, and we're going to turn it into like a small number of equations, which will say, wow, it's so much easier if I just have the equations. But in real life, we have text. So it's like, okay, we've got to practice our translation from English into math. Okay, so we're setting up a system of differential equations which model the amount of salt in a tank. There's a tank 1. So x is how much is in tank 1. And there's a tank 2. And y is in how much is in tank 2. So probably to help us, what should we do? Yeah. Pictures are great, and they don't have to be accurate. You don't have to be a good artist. So here is a picture, and I'll call this one tank 1. And then I'll say, oh, there's 2 tanks, so here's tank 2. Okay, so, and remember, we have x. That's our amount of salt in tank 1. Y, that's the amount of salt in tank 2. Okay, so far so good. We're like one line down. Assume both tanks are well mixed. That just means that, because there's salt in there, right? And so it's the same amount of salt regardless of what part of the tank you look in. It's equally salty water everywhere in the tank. Okay, next part. Tank 1 holds 50 gallons. Oh, we should write that down. 50 gallons. Okay. And initially has 200 pounds of salt. Okay, what does that mean? Initially has 200 pounds of salt. X0 equals 200. Tank 2 holds 250 gallons. All right, 250 gallons. Oh, well, okay, picture's not accurate, but that's okay. Initially has 50 pounds of salt. What does that mean? Y of 0 equals 50. So anytime you see initial, it says, okay, at time 0. All right. Now, there is 10 gallons per minute of fresh water continuously being pumped into tank 1. Okay, so we put something here. And here we got our water. This is 10 gallons per minute, fresh. All right, great. And 10 gallons per minute of brine continuously drained from tank 2. Now it's brine, so it's not going to be pure, clean water. Brine means there's some salt mixed in here. But again, 10 gallons per minute of our brine solution. Okay, good. We're almost there. There's one sentence to go. Hanging in there? Okay, the last sentence. In addition, there are pipes which pump 30 gallons per minute from tank 1 to tank 2. Okay, so there's a pipe here that runs in this direction at 30 gallons per minute, and which pump 20 gallons per minute from tank 2 to tank 1. So there's another pipe that runs that direction, and that's 20 gallons per minute. And then we come to here and say, wait, what was the question again? What was the question again? Do you remember? Yeah. This problem is so fun, we forgot what we were going to do. Okay, so we have the picture. Do we understand the picture? No. That's what the other class said. And I thought they were joking. Okay, what should we think of happening here? Is we have these two, we've done tank problems before like this, right? Where it's like that pours in. Now what we're saying is, oh, it's just we have these two tanks, they're mixing between themselves, and one tank has the intake, one tank has the out. Okay, so it's similar to the tank problems we've done in the past. But now instead of like one big tank, there's two separate tanks, and they're connected to each other. Let's talk about the flows. How much is coming into tank 1? 30, right? How much is leaving? 30. Is that a good thing? Yeah. Yeah, inflow equals outflow. So what happens to this 50 gallons? Stays the same. Let's go to tank 2. How much is coming in? 30. How much is leaving? 30. So what happens to this number, 250? Wow, you guys are good. You're really good. Now, let's talk about the change. X prime. So that's looking at tank 1. What's coming in that has salt? Only this part. The fresh water doesn't have salt. Okay, so the question is, how much salt is coming from tank 2? Somebody said 20Y, is that right? Someone said Y, is that right? Someone said 20 divided by 250? Is that right? So 20 divided by 250, the way we should think about that, that's how much of tank 2 is moving into tank 1 as a percentage. Now, how do we translate that into how much salt? You also need to multiply by Y. Is there any salt leaving? Yes. Yeah, out of this pipe off the bottom. How much? 30 over 50, because that's how much is in tank 1, times X. Y prime, how much is coming in, right? Because we're doing in, subtract out. How much comes in? This 30 over 50 times X. The only place that comes in is from tank 1. How much goes out? Now there's two places things go out. Do we need to separate them? No, because out is out. So there's a total of 30 leaving over 250, and there's Y. And then we'll throw in the initial conditions just for good measure, and then we say, look, here we go. Two equations, a system of two equations, and now what's the answer? Well, it doesn't ask us to do that. It just says set up. All right, that's it for today.